here. We started it on this. Where is the Zoom? We can close this, I guess. No, but you want to. Okay, so I think we should just get started. There is a lab due, so I think the number of students today may be less than usual, but it is an important class. So for those of you who are here, pay attention. I think there's quite a bit of new topics we are going to cover. Okay, so I hope you went to the guest lecture last time, which was on Monday. That was on sustainable computing. Okay? Now we are going to resume where we had left off 2 classes ago, which was we have started doing cluster scheduling. Today we will start talking about virtualization. Okay, so we'll have 3 parts to the lecture. I'll talk about the basics of virtualization first, then we'll talk about hypervisors, and then I will end with how do you virtualize resources? How does virtualization actually work when it comes to various resources? Okay, so let me start, but before I do that, let me finish the Borg material that I had left off when we ended the last class. So if you remember, we were talking about cluster scheduling. I'd introduced Mesos as one cluster scheduler. Then we started talking about Borg. Okay, Borg is Google's cluster scheduler. Okay? On all of Google's large data centers, Borg is the, or rather was, because there's now a new version of it. Borg was the scheduler that schedules all computation. Okay? Whether these are machines that run the search engine, whether these are machines that run their Gmail service, or their YouTube service, all of them get scheduled using Borg. Okay? And it's designed to run at very large scale, so you can schedule jobs on hundreds of thousands of jobs on tens of thousands of servers in a data set. So think about very large numbers of machines and even larger number of applications that are running on them. And Borg is responsible for deciding which applications run where, how many resources to give, and so on. Okay? Now, the ideas that originated in Borg essentially have later become Kubernetes. You will use Kubernetes in a lablet at least. We'll go through that in a couple of classes from now. You will use that in a lablet, okay? And then you will see what it is. But just keep that in mind, that these are ideas that sort of eventually became Kubernetes. So design goals for Borg were you want to do resource management at very high reliability. So because if Borg scheduler itself fails, then a lot of things that are running on the data center, they cannot do what they need to do. So many things will go wrong. So you want to operate with very high reliability because, as I said, it manages Gmail, web search, and so on. Needs to scale to very large clusters. But by and large, the idea is to run two types of job workloads: interactive workloads and job workloads, batch workloads rather. So all of the critical services that Google offers to outside users, they've come under interactive workloads because users are interacting with them. Okay, those are considered more critical. And in the background, Borg can also run many batch jobs. Okay, these could be just things that are being trained in the background or all kinds of other things that need to run. Okay, and batch jobs are given lower priority. So if interactive workload goes up, you essentially can even terminate some of the batch jobs, reclaim resources, and give them to interact. So interactive jobs always have higher priority in the Borg scheduler. Okay? And I'm going to put up a paper that gives this in more detail. Read it if you're interested. Okay? It's a good paper to read. Of course, I'm not expecting you to know a lot more than what I'm going to teach here, but it's a good paper to read anyway. Okay? So this is the architecture of Borg. So there are some terms to know. There's a term called cell. Cell is essentially all the machines in the cluster. As I said, there could be around 10,000 machines in each cell. Okay? And the job of the Borg scheduler is to match jobs to cells and machines. So Borg could be managing multiple cells. Okay? Each of them have about 10,000 machines. And then jobs come in, it has to find which cell will run it, which group of those cluster will run, and then which machine on the cluster will. Okay? And then the job could, of course, ask for more resources over time or less, and Borg will make this adjustment. Okay? The important thing that I mentioned just before we ended the last class is Borg is doing things differently from Mesos. In Mesos, we had the notion of a resource offer where the framework could not ask for resources. Mesos would just offer resources whenever it had some, and then the framework, which could be Spark or TensorFlow, would say yes or no. In this case, the tasks can themselves say, I need so many resources, and then Borg will allocate if there are resources. Okay? So that's the basic idea. Okay, so you have the Borg master, which is keeping track of everything, and then there are these Borglets. Those are the components that run on each machines that interact with the Borg master to basically make the jobs run and so on and so on. Okay? And the idea here was two things actually. One is the Borg master and the scheduler, the things in yellow, are the critical pieces that nearly need to run at high reliability because they manage these clusters that are running important application. So in Borg, these things are replicated 5 times. Okay? So there are essentially 5 versions of the Borg master running. So even if 4 of them fail, okay, there's still one that can run and continue to work. And these 5 can run on different regions, different locations. They don't run at one location because if a whole location goes down because there's a power outage, then of course all 5 will fail. So you replicate them, you replicate with a factor of 5. You use Paxos consensus to keep state so that you know what's happening on each machine. That's the state that Borg is going to maintain and so on. Okay? And then the other concept here is the notion of job priorities. So I said that I can run batch as well as interactive. Interactive workloads are given higher priority. And if there are not enough machines available, you can reclaim them from the batch job by terminating them and having them restart. Okay? So those are some of the high-level ideas in Borg. Okay? This is all I'm going to say about it here. So we'll now switch gears and talk about virtualization. Okay? So I'll give a very high-level introduction, okay? And then we'll start going into some of the details. Okay, so what does virtualization do? Okay, the idea of virtualization is to use one interface that some machine provides to emulate another interface, to mimic the behavior of a second interface. Okay? And this is shown, the very basic concept is shown in this figure. So assume that that's the original system you have. It has hardware type A, and maybe it runs some software system of type A, and the interface it provides is we will call that interface A to the program. Okay? Now you have another machine. Let's say it has a different type of hardware or software system B. It provides some other interface. Maybe it's a different type of architecture. This was Intel machine, that's ARM machine or something like that. So clearly a program that was designed to run here is not going to run as is on machine B, because the OS is different, the hardware is different, and so on. Okay, so it won't run as is. Now, if you could write a software layer on top of B that mimics the interface A that was on that previous machine, okay, then that software layer that is using interface B to mimic interface A is our virtualization layer. Okay, because we said virtualization is essentially taking one interface and using that native interface to mimic some other interface. So here we took interface B and we are mimicking interface A. Okay? Now, if you do this, the hope is that, and if you do this well, the program that was originally running on system A can run on B, even though B is actually a different type of system altogether. Okay? Is that clear, what I just said? So essentially, you want to use one type of interface to mimic another type of interface. And this idea originated actually many years ago, almost 60 years ago, in the 1970s, when mainframe computing was actually the real way you did computing. Okay? And mainframe machines were very expensive to buy, and there were only a few companies like IBM that used to sell them in those times. And of course, as technology improved, mainframe architecture systems improve. Okay? So you might think of some customer of a mainframe vendor that is running on machine A, and then after a few years they go and say, let's buy another machine because machine is getting old. Okay? So you go and then maybe you go to IBM or some other vendor and say, yes, we have a new model, it's much better, it runs much faster, it is now has all this new fancy architecture, the system B. And they'll say, by the way, nothing that was running on A will run on B because everything has changed. Okay? Now, from a customer standpoint, that's not good because they might have spent a lot of effort in building their own applications that run on machine A. Now, none of those will run, so they have to re-implement or port them to machine B if they buy another piece of hardware. Right? So that's not a good strategy. So instead, if you say you can buy a new machine, it's much faster, and by the way, all of your old applications will run as is, because I'm going to provide a software layer that will mimic your old machine. So everything that you wrote for machine A will continue to run on the new mainframe you buy. And then you can, of course, write new applications from this point on, but write them for machine B. Okay? So in this case, there is nothing that the customer has to do in terms of porting, because all of the applications just continue to run. So all the investment in writing applications are not going to go to waste. Okay? So that is how they basically sold their new hardware, because the hardware kept changing. And you needed to make sure there's essentially backward compatibility. And then you provided this layer, which is essentially a virtualization layer, to do this. And that is how virtualization technology arose. Okay? And that is what it was used for maybe 30 plus years. And then in the late 90s, I think there were new use cases for virtualization that came about, that you use them on desktops and servers. That is what we are going to actually discuss today. But this is the history of how it all started. Okay? So let me now give you some examples of what is this interface I was talking about that you want to emulate or mimic. Okay? So you can, there are many flavors of virtualization. Virtualization is not one thing. You will see that there are different types of virtualization, different flavors of virtualization, and they might differ in what is the interface that you are trying to mimic. Okay? So we'll talk about three types of interface. So that's a picture that shows these interfaces. So the lowest level interface is the machine interface. So this could be the CPU with the assembly instruction or the machine instructions on that CPU. So if you're emulating CPU instructions, then you have essentially one layer of emulation that's called hardware virtualization. So you're essentially emulating one hardware with using another hardware. Okay? That's called hardware virtualization. Okay? Now, you might also try to emulate at the OS level. Okay? That was emulating at the hardware level. So you might say, I don't want to do that. Instead, I'll take the operating system's interface and try to use that to emulate some other interface. Okay? If you do this, you have what is called OS level virtualization. So now you're essentially emulating system calls. One set of system calls is another set of system, because the OS interface is essentially a system call interface. Okay? Or you could say, I'm not even going to do that. I'm going to essentially take application level libraries and take one library interface to write another library that mimics some other interface. Right? So here now you are doing virtualization at the application level. So it's called application level virtualization. So you can have hardware level virtualization, OS level virtualization, application level virtualization. And what is different is what is the interface and what layers does that interface. So that's your hardware and software stack there, right? So in one case, you're emulating hardware, in another case, you're emulating OS interface, in another case, emulating application level interfaces. Is this clear, what I said? Okay, we are now going to get into details of some of these things. We'll start with the hardware virtualization here, and then we'll get to OS level virtualization. So if you just even take the hardware virtualization, there are many flavors of those. Okay, and I have two here, and there are some more on the next slide. The first one is called emulation. Okay, so emulation essentially is a software layer that emulates every aspect of a physical machine. Okay, think of I write a software emulator of a PC. Okay, so it emulates a processor of the PC, it emulates the memory, it emulates the disk, it emulates the network. So whatever hardware you have inside your laptop, you're going to take all of those components and think of them, you wrote a simulator for each of them, and you're essentially emulating them. Okay, but that emulation framework is your virtualization layer, and that's called emulation. Okay, so this is a very basic type of virtualization. So in this case, you have a lot of flexibility because you have your underlying hardware, which is some machine, you have your laptop or your PC, and your emulation framework can emulate any other type of hardware. It could emulate, you could have an x86 Intel machine, but what you're emulating could be an ARM processor and an ARM PC, or you could have some other type of processor. So the instructions that you're emulating or the processor that you're emulating could be completely different from the underlying hardware itself. Okay, so there's a question there. All right, so you're emulating entire hardware, and then on top of that hardware, because it's a full emulation of an actual machine, you can run an entire OS unmodified. You can actually boot an OS. Okay, and that OS will to the OS, it will look like it's running on a real piece of hardware, but it's actually running in an emulation framework. It's running on a software emulation of real hardware, not real hardware itself. But for the OS perspective, it will look like it's just interacting with real hardware because that's just emulated hardware. Okay? So you can run unmodified operating systems inside this piece of software. There are many examples I'm going to show you. One, the box virtual PC. There's a Linux framework called QEMU. I forgot what that acronym means. I'll look it up and tell you next time. And that's quite popular. I'll show you how that works as well. Okay? That's one type of virtualization. Okay? Another one is called full or native virtualization. Okay? So here, the interface so remember I said you have interface A and interface B. Interface B is the actual hardware interface in this case. And interface A is some interface you're trying to emulate. So if interface A and B are one and the same, okay, the interface you emulate is actually the same as the underlying interface, you have what is called full or native virtualization. Okay? So this means that your emulated PC, whatever you're emulating in software, is x86, and that software is actually running on a real x86 machine. Okay? So interface A and interface B are identical. In emulation, they are actually different because you can have a x86 Intel machine and you are emulating an ARM PC or something like that. Right? So in this case, they are one and the same. Okay? So you might ask, why do you need to emulate the underlying hardware if you already have it? And why would you run something inside the emulated VM rather than running that directly on the machine? Because they are the same processors, the same hardware type, and so on. Any thoughts? Yes. Is it for security reasons? So there is some security involved. You're right. But there are many reasons to do this. So let's say you want to run some test environment. Okay? You want to do something that could break the machine or some such thing. You want to run it in a sandboxed environment, which goes back to your security point. So you can do this on your full or native virtualization environment. So even if something goes wrong, your underlying PC is not impacted. Right? So there are many use cases, but that's just one of them. Okay? There are again many pieces of software There's one called Parallels that's available for the Mac. There's VirtualBox, there's open source for older Macs. There's VMware Workstation and many others. Okay, I'm going to show you some examples in just a moment. Okay, but let's go through the list. Okay, the third one is called para-virtualization. In para-virtualization, you are actually not simulating the hardware itself, but you will use a special interface to make a modified operating system, and that's the one that's going to run on your virtualization. In the previous two cases, emulation and full virtualization, you assume that you can run unmodified operating system. You can just take Windows and boot it up and it'll run fine. You can take Linux and boot it up and it'll run fine inside those virtualization environments. You don't need to change them. In para-virtualization, we actually make a special version of the OS kernel that is designed to run on that type of virtualization environment. Okay? Why we need it, we'll see in just a few slides. Okay? But if you have to modify the OS to run it on the emulated environment, you have para-virtualization. Okay? If you're running unmodified, you have native virtualization. So that's the real difference. Okay? And there is again Zen and ESX server. These are some products. We'll get to that in a few slides. Okay? And so those were all flavors of hardware virtualization. So we looked at emulation, native virtualization, and para-virtualization. They are all doing emulation of the assembly instructions of a processor. Okay, so that's actually at the hardware level. So next level up is OS virtualization. Okay, so here you are emulating the system call interface. Okay, if you have heard of Docker or Linux containers, those are all examples of OS level virtualization technologies. Okay, so in this case, you are not running additional copies of the OS. There's only one OS that you're running, and then you pretend that you're emulating the system call interface so that the application sees a different system call or OS interface than the native interface. But you're not starting another copy of the OS. In the previous case, you actually needed to run an entire OS inside that virtual machine. Okay? In this case, you're not going to run a new virtual machine. New operating system is the same one. You're just emulating the interface. Okay? And there are examples of this. Docker is the most common one today, but there are many that started this off. Solaris containers, BSD jails. Okay, there's Linux containers that are still used today and so on. Okay? And the last layer, or the topmost layer, is application level virtualization. So here you use some application level libraries to implement another interface. Okay? And there are many examples of this. The most common one that you should be already familiar with is the Java virtual machine. Okay? So Java programs run inside an abstract virtual machine. Okay? That virtual machine has some abstract concept of what a physical machine should look like. And that is the JVM framework is emulating a Java virtual machine using C libraries and other libraries. Okay? That's one example. Okay? If you know about WebAssembly or WASM, that's another example. And we'll talk more about that. That's trying to emulate another type of abstract virtual machine, just like Java. Okay? But there are other technologies. So there's one called Rosetta, which is actually an Apple technology. Okay? It has been used twice. Okay? Long back, Macs used to run on a PowerPC architecture. Okay? And then at some point, they switched to Intel architecture. So they basically just switched hardware architectures completely. Okay? So at that point, you had the same problem that I mentioned when we were talking about mainframe, right? So you might have written your applications on PowerPC. You might have purchased applications from others. Okay? Now, if you buy a new Mac, you have to say, throw it all out because nothing will run that on PowerPC is not going to run on Intel as is, right? Because it's completely different architecture, okay, even though they're both Mac. So what Apple did is they built this layer called Rosetta, okay, which basically allowed you to run unmodified applications developed for PowerPC on Intel architecture. Okay, you basically had the application look exactly the same. You just double-clicked it, it would run, but it was running on this emulation framework because that framework was translating on the fly PowerPC assembly instructions to x86 instruction and just executing them as the application was executing. So from your perspective as a user, it looked like the code just ran, even though it was developed for a different architecture. Okay? So they did that maybe 10, 15 years ago. Then a few years ago, they again came up with Rosetta 2 because they, if you know now, they switched from Intel back to ARM, which is Apple Silicon. Okay? Same problem. You might have an Intel Mac. Okay, you wrote some applications of your own. Maybe you bought some applications from some app store. Now you buy another Mac saying it's faster, but none of your applications. That's not good, right? So they basically did the same thing all over again. So now you have, if you have an Apple Silicon Mac, an M1 or M2 type Mac, it has Rosetta 2. So any Intel application actually runs as is. You don't even know that's an Intel application. Yeah, so it will run Intel code because it's doing binary translation of x86 instruction to ARM instruction on the fly. Okay? Another example of application level work. Yes, question. Okay. Question is an interpreter for Python and application level virtualization. So not technically, because it's not emulating a specific interface necessarily. That's just right. It's just running a program that's written for Python. Okay. You have to emulate some interface in some sense for you to call it virtualization. Otherwise, there's no difference between a programming language and virtualization. You can say is Java, not Java, C library also virtualization, right? Or is Python, it doesn't have to be an interpreter. The library does not have to be an interpreter. It's still a library that emulates some framework. Okay. Yeah. So question is, if you are using OS package, are you using virtualization? That's still not the case, because every programming language allows you an interface to invoke OS level system calls. That doesn't mean you are emulating the system call. Okay? In OS level virtualization, you can think of, you can write a Win32 emulator using Linux system call. Then you can run Windows programs on Linux, and there is a program called Wine. It's an open source program that does exactly that. It has a C re-implementation of Microsoft's Win32 library calls on Linux. So you can just run Windows application in that. So those are examples that would qualify, but not necessarily Python code. Okay. WebAssembly code, yes, because WebAssembly actually runs inside an abstract virtual machine. Okay. JVM, yes, for that reason, but not Python. So it's not just an interpreter, but you also need a virtual machine that you're emulating using the interpreter. Okay. Yes, question there. That's a good question. So if you use a virtual environment around Python, is that an example of virtualization? At that point, you start getting into some aspects of virtualization. I would say that's a lighter weight version of application level, because it is essentially pretending that you have a different environment and you're using that different environment, emulating that with something else. So those are some forms of virtualization. Doesn't cleanly fall into one of these, but is more like application level. Because it is emulating something. Anything else here? Okay. So I'm going to, after this slide, I will show you some examples so you can now understand how it was. But let's just give you a very high level introduction to how virtualization. Now we are back. I went through the entire layers, types of virtualization, and back to hardware virtualization. Okay. So here are two ways you can do hardware virtualization. Okay. They are called type 1 and type 2. They're just numbered. There's no meaning to this. So this is type 1 virtualization of hardware. This is type 2 virtualization. So what is the difference? So the virtualization layer in either of these cases is called a hypervisor. Okay? In some terminologies, it's also called the virtual machine monitor, or VMM. Okay? They mean the same thing. Hypervisor and VMM mean the same thing. We'll just use the term hypervisor. Hypervisor is a piece of software, okay, that's doing the virtualization of hardware. Okay? So in type 1 virtualization, what happens is when your machine starts up, when you power on the machine, okay, normally the OS is the thing that is going to start up on a normal machine. Okay? When you have type 1 virtualization, the hypervisor is the one that's going to start up, not an OS. So in some sense, the hypervisor has replaced the OS. The hypervisor is the one that boots up. It looks like an OS, but think of it as a very special OS that can only do virtualization. It's not designed to do anything else. You can't run some arbitrary application on that type of OS. So hypervisor is literally a special type of an OS that is designed to provide virtualization service. Okay? So if you have your hypervisor that runs on what is called bare metal, which means it's the thing that boots up when you power it on, That's called type 1 virtualization. Okay? Now that when you start up that piece of software, it will give you ability to create virtual machines. Each virtual machine is a full emulation of a physical machine. Okay? So in this picture, you see that as a type 1 hypervisor, there are two virtual machines you have started. Okay? In one virtual machine, you booted Windows. Okay? That's the OS you booted. That's the first one. And the other virtual machine, you booted Linux. Okay? So now your Windows and Linux, they're actually both running on the machine at the same time. Okay? When Windows run, it just looks two-way because Windows run inside a VM. That box that's surrounding Windows is the virtual machine or the VM. And that just looks to Windows as if it's a physical machine, but it's actually an emulated machine. Okay? It's not a real machine. Okay? The real machine is what the hypervisor is running. Okay? Same thing for Linux. Okay? It runs inside another VM. So you can create as many virtual machines as you want. So you can each can boot its own independent OS. Inside that OS, you can run whatever application you want. And then you have essentially now a type 1 virtualization environment. Okay, in this case, there are two OSs running, but you can have as many as you want. Okay, that is the first way to do it. The second way to do it is shown in the second figure. So this is type 2 virtualization. Okay, in type 2 virtualization, you will not boot a hypervisor, but you will boot some normal operating system. Let's say you boot Mac or you boot Windows or Linux. So you'll just boot up your normal OS. Okay? Now, on top of that OS, you are going to run a hypervisor. Okay? That hypervisor provides virtualization service. Okay? And then on top of that hypervisor, you can create as many VMs as you want, like the type 1 hypervisor. Okay? And so now there are multiple operating systems running in this case. There's the one that the machine booted on. That's called the host operating system. That's the one that's running on the physical host. Okay? That is this operating system. Okay, then you have your type 2 hypervisor. Then you created a VM in there. And then inside that VM, you have another OS that's running. That's called the guest operating system. Okay? And in this case, the host and the guest could be two different operating systems. This could be Mac. That could be Linux, for example. So you have Linux running on top of Mac inside a virtual machine. Okay? And you can have more than one of these. And since this is a normal operating system, you can have other applications running like you already have. You can have browsers running and your mail running and things of that sort. Okay? So these are two ways you can create virtual machines at the hardware level. Both are hardware level virtualization. Both VMs, okay, once they run on top of the hypervisor, they emulate a full-fledged machine. Okay? So they look exactly the same. The only difference is, in this case, there is no guest, there's no host OS. It's only the hypervisor that's doing virtualization and is acting like those. But in the other case, there is actually an OS running, hypervisor runs on top of it. All right? Okay. So I'm going to now show you a quick demo of some of these things. So I'll show you, because I already have Mac running, I can't run a type 1 hypervisor here clearly, but I'll show you a type 2 hypervisor. Okay, so I will start this thing called Parallels. It's a product you can buy. Okay, and here you see that I have actually 3 virtual machines. Okay, there is a okay, and I have Ubuntu 22, I have Ubuntu 20, I have BSD. But none of them are actually running, so they are actually all been suspended. But I can start one up. Okay, and it will start up. Okay, if I had not suspended it, would actually boot up from scratch, just as you're booting on a VM. But now you can see that I have actually a Linux machine running on my Mac. Okay, so the guest OS is Mac. Okay, so Parallels is made a VM. Okay, and then there's Linux running on this VM, and this essentially is native virtualization, which means that this Linux is an ARM version of Linux. Okay, so if you look at if I do uname, so you will see that it's going to say, I don't know if you can read it, you will see that it says AR64. That's basically ARM64. Okay, so Mac is ARM, Linux is also ARM. Okay, so the VM is essentially an ARM-based PC environment that's been provided to this, and you can run more than one. Right, so I could start another one. Okay, so now I have this one is BSD. Right, so now I have 2 virtual machines running at the same time. There's BSD. Okay, also ARM. There's Linux, Ubuntu, and then there is Mac. So now you can see there are 3 of these running. There's one guest, one host, 2 guests. Is that clear? Okay. So you could do this, let's say you want to develop on a Linux environment. You don't have to get a real Linux hardware. You can just create a virtual machine, run Linux on your laptop, and then you can just do whatever you want. Right? So that's an use case. It's used for development, it's for testing and all kinds of other things. Okay. I am going to suspend these. So now, so it's very easy to start and stop them. You can actually reboot them and then it'll just boot from scratch. But I just suspended them so they could start very easily. Okay? So that's one example. I'll show you another example because I talked about emulation, if you remember. Okay, this is just same the interface you're emulating is same as the underlying ARM on ARM, right? But you don't have to do that. You can actually do something else. Here's another virtualization environment. It's called UTM. It's free. Okay, and here I have actually 2 virtual machines. I'm going to show you. Okay? So here is a Debian Linux virtual machine, and you'll see if you can read it. It says x86. Okay, so this virtual machine is emulating an x86 PC on top of my Apple Mac, which is ARM. Okay? So you are essentially translating from x86 instruction to ARM instruction, and you'll see I can start it up. It will actually start from scratch. You'll see that it'll start booting up and whatnot, like you boot Linux, but it'll take a while. Okay? And the reason it's taking a while is that when you try to emulate some other architecture, you have to do on-the-fly translation. So that's going to be slow. Okay? In native virtualization, there's no real translation because if I want to execute some ARM instruction, it's the same as the underlying instruction. So you can just execute it natively. So native virtualization is always faster as a result. So you'll see the difference. This thing is still booting up, but if you do this on the other one that I was showing you, it will boot up much faster. Okay, so now it has actually started. Okay, so you will see now so I don't have a GUI on this one, but you will see that if I do this, you'll see it showing me x86. So this is essentially an x86 emulation, and this is using QEMU, which is that Linux environment that emulates, I think, 30, 40 different processor families of all kinds. So you can run any type of environment. Is this clear? Okay. All right, so I'm just going to stop this. And there another one which is actually native. That's an ARM, which I won't show you. So then it will just be ARM on ARM like the other case I'm showing. All right. So let us resume the lecture. So, all right. So here, let me ask the following question because sometimes I get this question. So you may have heard of dual boot machines. Okay. So it's worth asking, how is a dual boot machine different from virtualization? Is the question clear? You heard somebody's heard of dual boot machine, right? At least some of you have heard of. So can you explain the difference? Yes. Sorry? Yeah. So in a dual boot environment, what you have is you have installed 2 different operating systems on your disk. Okay? At boot time, you got to pick one of them. Okay? So you can pick A or B. Okay? But you can't run both at the same time. Right? Because at boot time, you say you can have a dual boot Windows Linux machine. So when you boot up, you either boot Windows or you boot Linux. Or you can have the same thing on a Mac, okay? And you can use the boot manager to decide. Okay? In a virtualization environment, you actually have more than one OS running, or you can have more than one OS. I just showed you examples where there's Mac and Linux running at the same time, and so on. That you can't do in dual boot. And you can pick one of the 2 if you had both of them installed. Okay? So you have actually 2 OSs running on your machine, and they can either run as host or guest, or they could just run as a bunch of guests. Is that clear? Yes. Okay, so question is there a overhead to running a type 1 hypervisor, or I was showing you examples of type 2 hypervisors because clearly my machine is running a host, which is Mac OS, and then I showed you all things running on top. I didn't show you any type 1 hypervisor, and the question is there a overhead for running type 1 hypervisor, right? So if you look at simply the software stack, you will see that there is less software layers in type 1 than type 2. So type 1 is actually going to be more efficient than type 2, because in type 2, you have to first run an OS, which is the host. Then you run a virtualization environment on top, and then you run a guest on top. Right? So now I have 3 layers here. I eliminated the host here. I just directly boot. So this boots up like a normal OS. Okay? It just doesn't look like a Windows. It just looks like a hypervisor that can start VMs. It can't do anything else. Right? So it's actually going to be more efficient to do this. But in this case, you can't run anything else other than VMs. Just think of it as an OS that can only run VMs and no other type of application. That's what it is actually. Okay, yes, question. Okay, question is, if it's more efficient, why can't the OS actually provide those services and boot it, right? So I'll have 2 answers to that question. First is, type 1 hypervisor is more efficient than type 2, but you should realize that just booting Windows directly on hardware is going to be more efficient than still running them on type 1. Okay? Because then you eliminated type 1 directly and you're just running Windows, right? So there's nothing you have to emulate, you're directly interacting with hardware. So running on bare metal an OS is going to be more efficient than running it inside a VM. Even in native virtualization, the overhead is minimal because instructions don't need translation, but there is some small overhead. It's not zero. Okay? So you could have just run Windows. Then you can't run anything else, but that's most efficient. Now, the second answer to your question is the way many of the type 1 hypervisors are implemented. Windows, for example, is a good one. It actually provides type 1 service as part of its OS service. Okay? I'll talk about that in just a minute when we talk about different types of type 1 hypervisor. So that is how many of them actually support it. But you can buy type 1 hypervisors that are not connected to any OS at all. They're commercial hypervisors, then you can run whatever you want on top of that. That is also available. All right. So before we talk about various kinds of type 1 hypervisor, here is essentially some high-level ideas of how all of this works. Okay? We'll start with type 1 first, then we'll get to type 2. Okay? So I'm going to get into a little bit of computer architecture stuff here for you to understand how type 1 virtualization is even implemented. Okay? So first, the basic concept you need to know about any processor is that processors have different modes that they can execute. Okay? By default, any processor has at least 2 modes. One is called user mode and the other is called kernel mode. Okay? So in user mode, only user programs are run, and in kernel mode, the OS kernel runs. So when the OS kernel is executing on the processor, okay, the processor bit is set to kernel mode. Okay? And when a user program is executing on that processor, the bit is set to user mode. Okay? And by and large, this allows the processor to determine based on what is running, what is allowed and what is disallowed. In kernel mode, because the OS is running and we trust the OS, everything is allowed. Okay? But in user mode, certain instructions are disabled. Okay? So if a program tries to execute certain instruction and the user mode is turned on, some instructions cannot be executed. Simple example is the halt instruction cannot be executed in user mode. Otherwise, any program can call halt and shut the machine down. Okay? That's an assembly instruction. That's only allowed in kernel mode. Only the OS is allowed to power down the machine. That's a simple example, but there are many other types of instructions that are only allowed in kernel mode. Okay? So that is the most basic type of processor, but there are other processors that allow gradations of trust. And as Intel uses this notion of rings. Okay? So rings basically means what mode it is. So user mode is essentially in Intel terminology, ring 3 is the least trusted and the most restrictive. And the kernel mode is ring 0, which is the most trusted and everything is allowed. Okay? But Intel also between user and kernel mode also allows ring 1 and ring 2. Ring 1 can do less than ring 0, but maybe more than what user programs can do and so on. So that's shown in this picture, by the way. So you will see in ring 0, you run the kernel. Okay? In ring 1, you can run device drivers. They are part of the kernel, okay? But they are third-party modules, so maybe you trust them a little less than the kernel itself. So you might put some restrictions because ring 1 will allow you to do somewhat less things than ring 0. And then the green thing is outside is ring 3. That is our user mode, where the least is the most restrictive. Okay? Many things are disallowed. Okay? So that's basically a quick introduction to computer architecture basics you need for what I'm going to say. None of that had to do anything with virtualization. That's just how processors are designed. But now let's just take user and kernel mode. You can forget about ring 1 and ring 2. So either you have ring 0 and 3, or we'll call them user and kernel mode. Okay? So here's how virtualization is going to work. So first thing is, we'll say that all the instructions that can execute only in kernel mode, which means only the OS kernel is allowed to execute it, we'll call them sensitive instructions. Okay? So sensitive instructions are disallowed in user mode, only allowed in kernel mode. Okay? So that's first terminology you need to know. Okay? Second terminology you need to know is something called privileged instruction. A privileged instruction is any instruction that causes a trap or an interrupt. There are many kinds of instructions that cause a trap. Like if you put a timer and the timer expires, it raises an interrupt. When something some event occurs, that can raise an interrupt. There are all kinds of instructions that will cause a trap. Okay? Any instruction that causes a trap, we'll call a privileged instruction. So two terminologies. Sensitive instructions are instructions that only the kernel is allowed to execute. Okay? Privileged instructions, any instruction that causes a trap. Okay? Now, there is a famous result that's was a theorem actually that said type 1 virtualization is only possible on a certain CPU, okay, if the sensitive instructions, okay, are essentially a subset of the privileged instruction, which means that sensitive instructions, every sensitive instruction also causes a trap. Okay? That's the result, and I'm going to explain why this is actually a result. Okay? So first, is that clear what I said here? So type 1 virtualization is only feasible on hardware or on processors where sensitive instructions are a subset of the privileged instruction. That's the result. Okay? Now let's try to understand why this is the case. So to understand this, let's take the previous picture here. Okay? We have type 1 hypervisor. Okay? There's no OS you booted up. So type 1 hypervisor is the kernel from the processor's perspective. It's going to run in kernel mode. Okay? Is that clear? Type 1 hypervisor is the one that's going to run in kernel mode. Everything else runs in user mode. Okay? So including that Windows that's sitting in the VM, that's now running in user mode, no longer running in kernel mode, because the kernel is the hypervisor. Okay? But as far as Windows is concerned, it doesn't know it's running in user mode. It thinks it's the OS. It thinks it's running on actual hardware, which is emulated. Okay? So it's still going to perform sensitive instructions, right? Because that's what Windows will do. If you run it on bare metal, it will basically try to do all kinds of sensitive instructions, access hardware, do I/O. You can do page table manipulations. All of these things are allowed in kernel mode. So Windows will continue to do this, but it's all happening in user mode. Okay? But what did I say? I said in user mode, sensitive instructions are disallowed. Right? So now Windows is just trying to do its job, but since you're running it in user mode, you'll find that none of the sensitive instructions work anymore, because they're disabled. They are basically, you put Windows is at a lower level of trust than the hypervisor. Hypervisor is running in kernel. Okay? You can't run Windows also in kernel mode, because then it will allow Windows to essentially wipe out the hypervisor and do arbitrary things. So you cannot run anything inside a VM in kernel mode. It has to run in user mode in this. So then you will say, how can Windows actually do its job if all of the sensitive instructions don't work in user mode? Yeah? And this is why that result is important. It says that it's feasible only if the sensitive instructions are also privileged instructions, which means that they cause a trap. Okay? So now let's say that condition is that property is true. Okay? Windows executes a sensitive instruction. Okay? And it's in user mode. So clearly in user mode is disallowed, but that instruction also causes a trap. Right? If you know anything about basics of operating system, what happens when a trap occurs? If a user application causes a trap, what happens? Yes, so trap essentially is like an interrupt, right? So it will switch into kernel mode and then the kernel handles it. So now Windows executed a sensitive instruction. It caused a trap. Okay, that trap will actually switch to kernel mode. So what will run now? The type 1 hypervisor is going to run, right? Because that's what is running in kernel mode. So the type 1 hypervisor will see the trap. It will see that Windows tried to do something that was sensitive, and then it will execute that sensitive instruction on behalf of Windows. Okay? And then return back to Windows. This is exactly how interrupts also work. When you application causes an interrupt, you trap into the kernel handles the interrupt, you go back to the application. So we are doing the same thing for the OS now. Okay? So this is how you will now run your guest operating systems inside virtual machines. They will run in user mode. They will continue to execute sensitive instructions, but you can now handle them at the hypervisor, because normally they would be ignored. So now we can actually cause a trap and handle them at the hypervisor. So if that was not true, then those sensitive instructions would not execute. In fact, in all x86 architecture, on Intel processors, sensitive instructions and user modes are simply ignored. It didn't cause a trap. Okay? You try to run a sensitive instruction application, the processor would not give you an error, would not cause a trap. It would just ignore it, saying you are not allowed. Okay? So early versions of Intel processors could not run type 1 hypervisor because this condition was clearly not true for them. Right? So because they were not designed to do this. Now, of course, later on, they added hardware support specifically for virtualization. So only Intel processors that have VT support, VT stands for virtualization technologies, and AMD processors that had the same property, they added this and called them SVM. I forget what S means. VM means virtual machine. Okay, allow virtualization. So what happens when you turn on VT? Essentially, your sensitive instructions are no longer ignored. They cause a trap. Okay? If you turn off VT on your processor, you can't boot a type 1 virtualization. You can boot a type 1 hypervisor, but you can't run anything on it because all sensitive instructions are ignored. Okay? But if VT is turned on in the BIOS setting, then you can, on that processor, you can run a type 1 hypervisor. Because, as I said, that condition actually has to be true. Okay? And I'm going to show you the same thing with the picture here, whatever I explained. Okay, so the gray box is your hardware. Okay? Then the thing that is running on top of it is your type 1 hypervisor. That's the one that's running in kernel mode. Okay? So in this type 1 hypervisor, you made a virtual machine, and inside the virtual machine, you are running a guest operating system. Let's say you're running Windows there, or Mac, or Linux, or something like that. Okay? Now, when that OS is running, it will cause some sensitive instructions. And because we said that instruction causes a trap, you will see that that causes a trap. The hypervisor starts running. It will handle that sensitive instruction on behalf of the OS and return back. So then Windows or whatever was running will assume that the instruction actually executed, and it will continue from that point on. Is this clear? Okay. So hypervisor is the real kernel in this case. Okay, upon trap, it executes your sensitive instructions, which were also the privileged instruction, or emulates them or something. It basically handles the trap. Okay. So this is essentially a property that you will need to implement a type 1 hypervisor. That clear? Okay. So now let's talk about type 2. Okay, before we do that, I'm going to give 2 examples. And then we'll get to type 2 hypervisor. So many examples of type 1 hypervisor. The one that is quite popular is built by VMware. It's called ESX server. So it's basically, you take ESX server, you boot it up, it acts as the kernel, and then you can type commands and start new VMs and so on. So you'll see you have a Linux VM, Windows VM, another Linux VM. Each of them run another OS. Okay, and this is basically going to execute exactly the way I said before. Okay. So that is one way you do type 1 hypervisors. In the Windows world, Windows actually now implements its own type 1 hypervisor, which is called Hyper-V. Okay? So there's a picture here. It looks quite complicated, but it's not very different from this or what I showed you previously. There is hardware, okay? And then on hardware, you have the hypervisor saying ring -1. I don't know why it says that. There's no such thing on actual processor, but that is the most trusted ring or the mode. And then on top of that, you can run the Windows kernel, you can run multiple partitions and so on. Okay? Now, this picture, although it shows this type 1 hypervisor in Windows actually running as part of Windows. It's not you're not booting Hyper-V and then booting Windows. You actually boot Hyper-V and Windows at the same time. Okay? Because they merge the two. So you have both the type 1 hypervisor and Windows booted, but this is the architectural view of it. The Windows is essentially running on top of a hypervisor, and then you can create additional partitions where you actually there is one Windows here and a second Windows here. You can of course run Linux and other things on this as well. Okay, so that is type 1 technology, hypervisor technology in the Windows world. Okay, I'll show you now how Linux will handle it. Okay. So Linux essentially does not have a very clean framework to do type 1 hypervisor. Okay. So what happens in Linux is they've essentially, just as Windows implemented Hyper-V as part of Windows, Linux has gone one step further, and they have a technology called KVM, or called kernel virtual machine, that has actually a module inside Linux. Okay. So you don't boot KVM as a type 1 hypervisor and run Linux on top of it. You essentially boot Linux. So Linux is your OS, but it has a module that is responsible for doing type 1 virtualization that's running inside the kernel. So Linux will provide other services as a general purpose OS. It will also provide KVM service to run other hypervisors or other virtual machines. Okay? And then what you do is you create a virtual machine using QEMU as the virtualization technology that can emulate other processors, or it could do native and things like that. So this combination of KVM, which is a module inside Linux, and QEMU is used to create virtual machines in a Linux environment, just as Hyper-V allows you to do it. But you will see that the picture is a bit muddled. It's no longer clean. It's not like you booted KVM, then ran Linux or some other OS. So you essentially booted Linux, and KVM is kind of now added as a new functionality. So it's general purpose OS plus type 1 hypervisor at the same time. Right? There are other examples for Chrome and so on, which I'm going to ignore here. Yes, question. Okay, so that's a good question. The question is, isn't this more like a type 2 hypervisor? It is somewhere between a real type 1 hypervisor and a type 2 hypervisor, because in a type 2 hypervisor, the OS itself does not provide any virtualization support. We'll talk about that on the next slide. All the virtualization is happening in application space. Okay? So if you go back to the picture I showed you, okay? So you have your host OS. Type 2 is running on top. There's no support that the OS has to provide for virtualization in this case. It's actually the type 2 hypervisor is an application that's running. Okay? And then you run VMs on top of it. So this is more like a hybrid of the two. Okay, but it's a good question. And now let's talk about type 2 hypervisors. So how are they going to work? So what is the picture to keep in mind in the type 2 hypervisor? You boot your normal OS on your laptop. You start an application. It's Parallels, which is the one I showed you, or you can use VMware Fusion or VMware Workstation. That starts as an application. That application is actually a hypervisor. It's not a normal application. That application allows you to create other VMs, and then inside those VMs, you're going to run a host, a guest operating system. Okay? The same thing holds what I said before. The Windows that's running inside the VM still things is running on physical hardware. It's still going to make sensitive instructions. Okay? Now, in this case, your type 2 hypervisor is not running in kernel mode. It's a normal application. It's also running in user mode. Right? So the trick we used for type 1 no longer applies, because there your guest OS makes a sensitive instruction. You trap to the hypervisor, hypervisor handles it. Here, you execute a sensitive instruction. The hypervisor has no more privileges than you. It's also an application process, just like Windows is running in user mode. So it can't actually handle privilege instruction. So that technique is not going to work in this case. Okay? So what type 2 hypervisors, the way they implement virtualization is the following. So When they load the OS code, they start scanning the code of the OS. Okay? If they encounter a sensitive instruction in that code, okay, the type 2 hypervisor will dynamically replace that instruction with a function call. Okay? So you are essentially doing dynamic translations called binary translation. So you just scan the code because you cannot allow the OS to execute a sensitive instruction because type 2 hypervisors can't handle it. They're not running in kernel. So what will you do? You will essentially try to scan the code on the fly as the Windows or Linux is executing. Every time you see that there is a sensitive instruction that's going to be executed soon, you will go and replace that instruction on the fly. Okay, you look at the instruction and replace with the equivalent function call. Okay, so when then Windows makes the function call, that function call will actually call the VM library. Okay, and then the VM library will make a system call to the OS, the regular way, like any application, make a system call and do whatever the sensitive instruction needed. Okay, so this is what you're going to do. So this requires that you're continuously scanning the code and looking for these instructions and then translating them on the fly using function calls. And then the function calls will call the hypervisor. A different way of implementing virtualization and handling sensitive instructions that are executing in OSs that are running in user. Is that clear? Any questions here? All right. So there are many examples. I showed you parallels. Okay, so that was the one that was running Linux. That is what it's doing. That's how it's handling all of this. Okay? But let's now talk about para-virtualization, and you will see the difference. Okay? So type 2 virtualization essentially took sensitive instructions and replaced them at runtime on the fly. Okay? But you could say, why can't I do this at design time? I can actually take the code, source code of my operating system. Okay? I, as a kernel developer, software developer, look for all of these sensitive instructions that are inside my kernel. But not every instruction that the kernel does is sensitive, right? Only some of them will be sensitive. So I can look for them, and I can actually rewrite them using function calls, same as what was happening at runtime. Okay? If you do this, now the operating system has changed. In the previous case, you could run unmodified OSs. You could just take a Linux binary and boot it up, and it would just run. In this case, you are changing the source code of the operating system by going and replacing every sensitive instruction that's present with a special function call, which we'll call a hypercall. Okay? And then you boot this OS. Okay? So every time it executes a sensitive instruction, it's going to make a hypercall. And as you can imagine, a hypercall is going to call the hypervisor. Just as a system call calls the operating system, the hypercall is going to call the hypervisor. And then you essentially handle whatever it's doing inside the hypervisor. Okay? If you did this, now you can run type 1 hypervisors on any hardware that you want. And that property I was telling you about, where the sensitive instruction needed to cause a trap, no longer applies. Because all the sensitive instructions are gone. There is no sensitive instruction left inside the OS. You replace them. Okay? And you recompile the OS. So the OS this is now a new OS that you modify. This modified OS has no sensitive instruction. It only has a set of hypercalls that have replaced the sensitive instructions. And those hypercalls are explicitly calling the hypervisor. Okay? In the previous case, they are causing a trap and calling the hypervisor. Now you make an explicit call. Okay? So if you do this, then I don't need any sensitive instruction to have the ability to have a trap. So now you can run type 1 hypervisor even on older hardware where that property is no longer true. If you can run on old Intel hardware, okay, this type 1 hypervisor, this is called para-virtualization. So you run a para-virtualized OS. Okay? And if you run a para-virtualized OS, you can run type 1 hypervisor on any type of hardware. Doesn't matter. Because all the sensitive instruction properties are gone. There are none left inside the OS you're running. Is that clear? Okay. So para-virtualization is a way around the limitations of this type 1 hypervisor, which could not run on certain types of hardware. So the processor did not support that property, right? Because you needed that property where sensitive instruction cause a trap. So OS designer said, let's change the OS. Instead of changing the hardware to have that property, we can change the OS to not require the property. And then you get hypervisors that can run on any hardware. Okay. But the downside is you need access to the source code of the OS and you need to modify it. So you can't take Windows and run it because you will not, as a user or a developer, unless you're Microsoft, not have access to source. But for Linux, sure, it's an open source kernel, so you can develop para-virtualized Linux. Any open source operating system, you can make it para-virtualized. The commercial ones, you then require the vendor to give you one that's para-virtualized. If they don't have one, you can't run it. Okay, all right. That is para-virtualization. Here's an example of a system that was quite popular at this time that did exactly this for Linux. It was called the Zen hypervisor. Essentially, it was a type 1 hypervisor. This is your hypervisor layer. That's your hardware. That's the hypervisor layer. Okay? And then you essentially ran Linux versions that were all para-virtualized. Okay? Because you could, this would run on any hardware. It did not require you to have any special VT support on your processor or anything like that. Okay? So it was a good open source software. It still exists today, but because today's processors by and large support virtualization technologies, you don't need to do this. You can essentially run unmodified OSs. You don't need to run a para-virtualized version now anymore. Okay? But still open source projects are still available. So you will see essentially the architecture of this. The interesting thing here was there's a special VM that this ran that essentially hosted all the device drivers, and those were handled specially, so you didn't have to do all of the device driver work in the para-virtualized code. If you needed to make a device driver call, the para-virtualized code did not make a hyper call to the hypervisor. It made a call to the special VM, which was called a domain 0 VM. And domain 0 VM handled all the IO for it. Okay? So they basically routed all the calls. Rather than making hypercall, they sent it to another VM. That VM had all the special code that you trusted to make the calls. Okay? So they did some extra things that go beyond what I showed on the previous slide to make it all work. Right? I will point you also to a paper on Zen if you're interested. You can. It's an old paper, but it's a nicely written one where you can get some more details of how this all works. All right. Okay, so the time that we have left, 10 or so minutes, I'll talk a little bit about, we have by and large talked about hardware virtualization today, but mostly focused on the processor, the instructions and the fact that they're sensitive instruction, not, and so on. But remember, we are emulating the entire machine. You've got to emulate the memory, you've got to emulate the disk, you've got to emulate the network card. We didn't talk about how any of that was. We only talked about how can you emulate the processor, which is clearly an important part of the machine. But that's not going to be enough, right? You've got to emulate everything else as well. So I'll briefly go into how do you virtualize memory and how do you virtualize disk and so on. Okay? So in memory virtualization is going to require similar ideas to what we talked about in processor virtualization. So you're emulating memory, but if you have Windows that's trying to now, let's say, change page tables for the processes that it's managing and so on, those are going to be all sensitive instructions. Because page tables on hardware can be only modified by the kernel. Application processes are not allowed to muck around with page tables or anything like that. Okay? So you need some similar way to handle accesses to page table, to modify them and so on. So the way you do this is the hypervisor essentially keeps a shadow version of the page table. And then there is one that's managed by Windows, that Windows is managing. And there's a mirror of it, which is called a shadow page table that's inside the hypervisor. Okay? And the page table that Windows manages is essentially read-only. Okay? So when Windows tries to modify it, it's trying to write to a read-only page table. That's going to cause a trap because you can't write to a read-only page. Okay? So then you come to the hypervisor, then the hypervisor tries to see what is going on, and then it modifies the shadow page table and projects that back to the original page table. So then the page table actually gets that modification, but the hypervisor is making that change for you because Windows by itself cannot. Okay? So you make these extra tricks to do all of the work because it's essentially saying the hypervisor has to do the work because Windows, which is running in user mode, cannot actually go and make page table changes and so on. So virtualized memory You will have to still offload your sensitive work to the hypervisor, and this is how you do it for the memory. Okay? So that's all I'm going to say. There are lots of details I glossed over, but you really don't need to get into all of that because you just need to know at a very high level. You have to virtualize memory as well. There's something called shadow page tables that you will use in the hypervisor to make the mapping between the actual one and the one inside the hypervisor. Okay. I/O virtualization is actually much easier, and you will see this. You will have a lablet in maybe a few weeks, which will be on virtualization. And you will see how I/O virtualization works. Okay. So in I/O virtualization, you are emulating the disk. Okay. So you have a physical disk on your machine, and it has a file system, let's say. Okay. Now, your virtual machine or Windows or Linux thinks it is going to manage its own disk. Okay. But you don't want it to manage the physical disk, because the physical disk should be under the control of either type 1 hypervisor, or it should be under control of your guest operating system. So on this machine, my Mac OS is going to manage the disk. If I run Linux inside a VM, it's not going to get access to the full disk and do whatever it wants. Okay? But it still thinks it has to manage a disk because that's how it's built. Okay? So what are we going to do? We are going to create large files, okay, and then make this file look like disks to the OS. Okay? And we'll call this files virtual disks. Okay? A virtual disk, the way it's implemented, is just a large file. So you can make, let's say, 10 gigabyte, 10 GB file, okay, on your machine. Okay? Initially, the file will be empty, just as the disk is empty when you start with the OS. It will be an empty 10 GB file. Okay? Then you want to install the OS, you want to install program, you will slowly start filling this file with all of that data. Okay? But this file will appear to the OS, okay, as if it's a disk. So when it's reading and writing to disk blocks, underneath, okay, you are reading and writing to parts of a file. Okay? But the OS doesn't know it. It just thinks it's reading and writing to a file, a disk. But you are essentially going to use files and make them look like disk to the OS. Okay? That's a simple way you can essentially emulate disks by not actually having to have real disks. You just keep containers of data which are files and then make them look like disks. Okay? So that's essentially how you're going to emulate this. So you will see when you create virtual machines, you have to essentially create what is called a virtual disk file. Okay? It will say when you want to create a virtual machine, how much storage space do you want to give to this VM? Let's say you say 10 GB. It will create a large 10 GB file on your machine. Okay? That file will start off as empty, and when you install the OS, all the OS installation will happen inside that file, just as when you install it on a real disk, you put it on a disk. Okay? And then you'll see the file starts filling up, and but when you boot it up, it looks like a VM. So essentially, that's a virtual disk file. The interesting thing about a virtual disk file is all of the data that the OS and the applications that ran on it are all inside that one file. Okay? So you could actually take that virtual disk file and copy it over to another machine, okay, and boot the VM there, because the OS code moved, the data moved, and the VM will boot there, and all your data is still there. Okay? Which is not possible to do very easily. If you want to take what's on your laptop and move the data, you have to do a migration. And so here it's very simple. It's like the file copy. Okay? So if there is a hardware fault, let's say on one machine, you just have to move the virtual disk file to some other machine and then boot up the VM there, and everything is good. Okay? So VMs will give you some advantages for migration that we'll talk about. Having virtual disk is one of those benefits that we will use. Okay. All right. So that is I/O virtualization. Yeah, I didn't say much about network virtualization, but let me also mention that. So every machine will have either an Ethernet card or a Wi-Fi card that is going to use to communicate. Okay. And virtual machines also need the ability to communicate, because maybe Linux is going to communicate with some other node or so on. Or for your lab, you might set up two VMs. One of them runs the client code, the other runs the server code, and you can have the two VMs communicate. You don't actually need to go to the Ed lab. If you know what you're doing, you could simply start two VMs on your laptop and run the client code in one, server code in one, and you have to make sure the networking works right, and then you can communicate, and it'll just communicate over a virtual network. Okay? So you still have to emulate a network in this case. So what happens is, most of the time you will essentially have what is called a logical network card that you have exposed to the virtual machine. It looks like an Ethernet card. It's not a real Ethernet card at all. Okay? Just a logical emulation of an Ethernet card. And when you try to send data, let's say you make an RPC call, you make a socket, or you run a browser that's trying to communicate, data is going to go to that logical Ethernet card. Okay? What the hypervisor will do is will just take that data and pass it on directly to the physical card. Okay? And the physical card will send it on. As far as the physical card is concerned, some process somewhere on the machine generated some packets, and they're just going out on the net. Okay? But you have to do some translation, okay? Because the IP address of your physical card may be different from whatever IP address you assign to the virtual machine. Okay? So some extra translation has to happen. But essentially, you will use the physical card, okay, to back up whatever is happening on the operations on the virtual network card, essentially eventually become operations on the physical card. Okay, but you can't directly access the physical card. You only read or write data or send or receive data on the logical card. The hypervisor is just sending them back and forth. Okay? And that way you will essentially get communication functionality as well. Yes, question. Okay. So, yeah. So the question is, let's say you ran two VMs for your lab on the same machine. Okay. And you ran the client code in one, the server code in another, and then the client is sending some data to the server. Do the packets actually go out on the network or not? That's what you're asking. So in this case, the packets actually do not go out on the network. What will happen is the packets will go from the logical card to the physical card. Okay? The physical card is actually going to see the destination address of where the packet is supposed to go. If the destination address is same as the source address, say this packet is actually going back up to something else on the same machine, it does not need to go back out. So it will basically go back up as if it arrived from the network. You don't have to send it back and come back up, but it does go down the protocol stack and then come back up saying the sender and the receiver are the same machine. So I don't need to actually send it out. I just send it back. That's what is going to happen in this case. Right? Okay. All right. So we have a minute left. Let me just start wrapping up. So there are many use cases of virtualization. You will see that one of the advantages, and this is same for Docker, by the way, is that you can get virtual machine images. Those are pre-packaged virtual machines that have an OS and some application pre-installed on them. Okay? You can just get the image. It's like a virtual disk file. Right? So you just copy the image and then you boot the machine. And then the machine comes up, the OS runs, and then whatever application was installed on it starts running. So this is a new way of delivering software where you don't say download the software, install the software, do all of this configuration, and then the software starts to work. You get a pre-configured VM, okay? And you just download and run it. Okay? And the same thing in Docker. Okay? Docker actually made this even easier. You have pre-configured Docker image. It's basically an application that's pre-configured. You just download it and you run it, and it just starts running. So it saves you the headache of installing and configuring things because you are essentially able to get pre-packaged, configured software. Okay? So this has become a new way to distribute software, either through VMs or through OS containers like Docker and so on. So that those are all called virtual appliances. Okay? A virtual appliance is just a virtual machine that comes pre-installed with some OS and some software in it so that you can just download and run. Okay? And there are many other use cases, and we'll get to them. So data centers make heavy use of virtualization. They all run type 1 hypervisors. Okay? That way, each server, which might have 64 cores, 128 cores, doesn't have to run one machine, one OS. It can run multiple OSs with different applications. So you can run all kinds of applications, each inside their own OS on that server. So virtualization is essentially a good use case for data centers. Cloud computing is all built on virtualization. If you go to a cloud provider and say, give me a machine, they're not actually giving a physical machine, they're giving a virtual machine. So they just boot up a VM and just hand you the SSH key, and then you can just log into it. Okay? So that's basically another use case. And the reason is they don't really want you to be running an OS on their machine because you are root system admin on your OS and you can do something malicious. But if you run inside a VM, that's more control. Okay, they can essentially pause you or do something to make sure that VM doesn't do malicious. Okay, so cloud computing uses virtual machine. Desktop computing uses virtual machine. I just showed you use cases. You can use it for testing your lab code. You can use it to develop code. If you want to develop Linux code but don't have a Linux machine, make a virtual machine and then you have a Linux machine. You don't need to go get another hardware to run it and so on. Okay, so it's run for tests and dev. It's run for you running apps on another platform. So all kinds of use cases. Okay, so we'll talk about this in more detail. I just wanted to give you some examples of where all of this is used. Okay, so next time we'll start talking about OS virtualization, and then we'll look at cloud data center virtualization and things of that. Right. So let's stop here today. We'll continue next time.